Guys, Mr. Carlson here. Let's talk about something called kinetic molecular theory. And what this is this is basically a theory that describes the behavior of an ideal gas. You know, we keep using this term ideal gas throughout this unit. We haven't really dove too deep into talking about what it really means. So when we use this term ideal gas, it's really it's a hypothetical gas. It's something that's not real, essentially. An ideal gas is like the perfect gas, which is technically not possible. So it's a hypothetical gas. It's not possible, technically, and it's not real. But the thing is even though this idea of an ideal gas is technically not possible, we can still use the assumptions of this kinetic molecular theory. We can still use its assumptions to help explain the behavior of real gases under certain conditions, basically. So what we want to understand is that some of these assumptions that we talk about this kinetic molecular theory, technically aren't possible with a real gas. It's just with a hypothetical gas. But the thing is that under certain conditions, most gases will kind of get close to this ideal gas behavior. They'll get close to acting like this ideal hypothetical gas under certain conditions. So let's first talk about what are these assumptions that we make about these ideal gases, or in other words, what's the assumptions or the postulates of this kinetic molecular theory. And some of these we've already touched on, and some of them we haven't. But let's look first at the first postulate of kinetic molecular theory, which is that the particles are so small compared with the distance between them that the volume of the individual particles can assume to be negligible. And essentially, and in this first postulate here, we can kind of see how this really isn't possible, because it's saying that we're assuming when we look at a gas and we start to try to understand its behavior, what we're assuming is we're assuming that the individual particles of this gas are basically, they have no volume. So we're assuming that the volume of these particles is zero, which, right, that's technically not possible. If I come over to this simulation that we've been using, right? Let me put some particles into this container. What that first postulate is saying is that we can assume that because the size of these particles, and again, this obviously isn't drawn to scale, but with real gases, we can assume that these are so small compared to the size of the container and the size of the distance between the particles, that we can just essentially say that their size is negligible, that we don't really have to take them into consideration. But obviously, those particles do have some volume, they do have some size, but they're so small that we can kind of make that assumption that they don't have any volume, and we can still kind of look at the behavior of those particles. So that's the first postulate of kinetic molecular theory, is that we're assuming the volume of the particles to be negligible, meaning zero, meaning we don't have to take them into consideration. Second postulate of kinetic molecular theory: the particles are in constant motion, and the collisions of the particles with the walls of the container are the cause of the pressure exerted by the gas. This is something we have already touched on at the beginning of the chapter. We talked about how whenever we're dealing with a gas, we assume that every single particle is always moving, and that the pressure that the container feels is due to the force of those particles hitting the walls of the container. So again, if we come back here, this is measuring the pressure the entire time, and that pressure is coming from every time one of these molecules hits the side of the container, and that's what causes the pressure. And these are always moving and in constant random motion. So that's the second part of that. Third part: The particles are assumed to exert no forces on each other. Now you got to be careful here because we just talked about up here that they collide with each other. So they're exerting, when they collide with each other, we can think of that as a force. But what this is talking about here is these attractions. So kind of like we can think of those like magnetic attractions, kind of, sort of like that. It's saying that we assume that they don't attract or repel each other. They do not attract or repel each other. So if we come back to here, when they are colliding with each other, there's no forces of attraction or repulsion with each other. So it's not like as they come close, we're assuming that when these molecules get close to each other, they're not going to, because of their positive and negative charges that they may or may not have, we're assuming that they don't attract each other and that they don't repel each other, which again, with real gases and with real molecules, we know that some of these things have positive or negative charges and that they do actually exhibit some forces of attraction. And we'll talk about that here in a little bit. But with this ideal gas behavior, we assume that they don't attract or repel each other. And the last thing here, the average kinetic energy of a collection of gas particles is assumed to be directly proportional to the Kelvin temperature. Again, this is something we talked about in the previous video, is that as I increase the temperature, I'm increasing the kinetic energy of those particles. Now, here's the thing. So all of these are assumptions that we make that we know aren't technically fully true, right? But they're true enough in a sense that it helps us explain real gases. So let's talk about real gases for a second. If we look at real gases, a real gas typically exhibits behavior that is closest to ideal at low pressures and high temperatures. So if I take a sample of gas of, let's say, like nitrogen gas, okay, N2 gas, what I'll notice is that it will exhibit this ideal gas behavior, this perfect hypothetical gas behavior, when I keep this gas at very low pressures and high temperatures. Now, why? We want to think about why is that? Why would that be that the closer I get to a very low pressure or a very high temperature is when these gases begin to give us this behavior of ideal. So let's think about low pressure versus high pressure, for example. If I have something that's in low pressure, if I have a gas that's in a low pressure, well, with low pressure, we can think of it kind of like the molecules aren't very, they're not pushed together as much, right? They're not forced to be together as much. It's low pressure, and so molecules are not pushed together, we'll say, as much. Pushed together as much. And so therefore, as they're moving around, we can think of it as they're moving around. Here's these molecules moving around in here. And let's say I decrease the pressure by making this bigger. Okay, so I'm dropping the pressure by changing the volume here. But so the pressure has dropped down to 7.8. Whereas I think it was up to like 12 before. Yeah, somewhere around 12. So if I think about it, now they've kind of, each of these molecules in here, if I drop the pressure like that, they've got a little more room. They're not as pushed together. And so as they move around, they can kind of overcome those attractions that they have between each other. So let's come back over here. So molecules are not pushed together as much, so they can overcome attractions that they have towards each other. Oops, attractions. But if I have something if I increase the pressure on it, a higher pressure, now the molecules are pushed closer together. Molecules are pushed closer together. And so now, since they're closer together, it's harder to overcome those attractions. So that's why if I've got a gas that's at a lower pressure, it exhibits that behavior that's closer to ideal than if I've got it at a higher pressure. So the higher the pressure, the farther from that ideal behavior that gas starts to act. What about high versus low temperature? Well, let's think about it in the same terms of these attractions, right? Well, if I have something at a high temperature, that means I got these molecules that are moving very fast, very high velocities, right? They're zooming around at, most of them are zooming around at very high velocities. So let's come back over here. If I increase the temperature, we know that those particles are going to start to move faster and faster and faster. And so let's think about this. If I'm a particle in there moving faster and faster, it's going to be a lot easier if I'm zooming by another particle really quickly. It's going to be a lot easier for me to overcome the attraction to that other particle as I go really fast by it. But if I'm going kind of slowly by it, it's going to be a lot harder to overcome those attractions between those particles. So in this case here, again, easier to overcome those intermolecular forces, easier to overcome attractions to each other. But at low temperatures, now I've got these molecules, they're not traveling very fast, much slower velocities, and so as they pass by each other, it's going to be harder to overcome attractions. And so that's why at a lower temperature, this gas will start to deviate further and further from that ideal behavior, because remember, one of the assumptions that we had up here was this right here, number 3, that the particles are assumed to exert no forces on each other, which is not the case with real gases. With real gases, they have these intermolecular forces on each other of attraction and repulsion, and so that's why we see what we see here. Now let's take that one step further. So IMFs and polarity. So IMFs just means intermolecular forces. Intermolecular forces. Just those forces of attraction between these different molecules. So let's take, for example, an H2O molecule. If I were to draw out what an H2O molecule looks like, here it is. 2 hydrogens attached to 1 oxygen. Now here's the thing though, we got to talk about polarity here, because certain molecules have a much stronger attraction towards each other than other molecules. So if I had a bucket of water basically, and I were to zoom in and look at each individual molecule of water, I would see that oxygen, because it's much more electronegative than hydrogen, kind of pulls these electrons away from hydrogen, and those electrons spend a lot more time over here with oxygen, and so oxygen has an overall negative charge in this molecule, whereas the hydrogen molecules have an overall positive charge. And so this is kind of a polar molecule, so it's this side of that molecule is kind of negatively charged, this side of the molecule is kind of positively charged, and so what we end up seeing here is right now this hydrogen, another water molecule that's over here. Another water molecule that's over here. Again, positive side, negative side. And so these two things are attracted to each other. These two molecules are attracted to each other because of this positive side of the water molecule here, the negative side of the water molecule here. They attract each other. And that's what we would see throughout the whole bucket of water. All these water molecules would be like that. Here's another water molecule like this. The positive side of this hydrogen attracted to the oxygen here, and we could keep going like that. And so within that bucket of water, I get these polar bonds here, these polar bonds. But let's say I took something like hydrogen by itself, just hydrogen, plain old hydrogen gas. Well, hydrogen we know is diatomic, which is one hydrogen attached to another hydrogen like this. Now let's think about the bonds between some H2 molecules. So here's some H2 molecules floating around here. The attraction that there is between H2 like this is not as strong because this is a non-polar bond. Because H2 here is not like water where part of it is going to have this positive side and part of it's going to have this negative side. H2 really doesn't have that because they're both hydrogens, and so the electrons spend equal amount of time around each other, and so we don't really get this polarity like we have over here. And so with this diatomic gas, this would be a nonpolar bond. And so therefore this over here is a much stronger attraction. Stronger attraction. This over here is a weaker attraction. And so if we have, let's say we had this water and we heated it up enough to break these polar bonds and we keep it as a gas, it's going, this molecules, this water, this H2O water vapor, is not going to exhibit ideal behavior as much as this H2 gas is going to, right? Because this H2 gas doesn't really have these strong attractions like these polar bonds do. And so because this is a non-polar molecule, this will exhibit more ideal behavior, or it'll be closer to ideal behavior than this will. So like for example, if you see a question that says which gas will behave more ideally, will it be H2O or water vapor or O2 gas? Well, you know that H2O is going to be a polar molecule, and O2 again is just going to be like H2. It's going to be this non-polar bond, and so you know that O2 would have more ideal behavior, or be closer to ideal behavior, because, wait, that sentence doesn't make sense. Would have more ideal behavior because is a non-polar, because is a non-polar molecule. And so there's less attraction between molecules. So hopefully this makes a little bit of sense when we're talking about these different things that we assume for kinetic molecular theory, and why it is that for real gases, why it is that certain ones exhibit behavior that's closer to ideal, and then others that are not so close to ideal, and under which conditions they do that.